Hello everyone, welcome. I know the video was being blurry for the pear deck, so I'm just redoing this right now. This is the start to our second lesson, NQ2. So you're opening up that pear deck assignment and you're going to be working through radical expressions and rational exponents, okay? So put your name on that first slide, and when you're all set, push ahead to slide 2. Now slide 2 is just looking at some of our important vocabulary. So we have write each vocabulary term in the correct place in the sentence frame. So I'm going to use my little text tool option in the pear deck. You can use that as well. So it says blank a number means raising the number to the second power. So when we're raising something to the second power, we are squaring a number, okay? And the opposite or inverse is taking the square root. Beautiful. We see this symbol. We see it on our calculator. And that is the symbol that is used for the square root symbol. Numbers with whole number square roots are called perfect squares, and we're going to go through what that perfect square list is together. And the inverse of cubing a number is taking the cube root, and a number with a whole number cube root is called a perfect cube. So cubing and cube root, that all has the power or the root of 3 versus squaring and square root, which has that power and root of 2. And I know we talked a little bit about exponents last week with order of operations, but we're going to keep doing that. Keep looking at those roots and squares and exponents and powers throughout this week as well. Okay. So what is a perfect square? A perfect square is a product, right? So we're multiplying of 2 equal integers. So a perfect square example is 4, because 2 times 2 is 4. 9 is a perfect square because 3 times 3 is 9. 36 is a perfect square because 6 times 6 is 36. Okay? The square root of a perfect square just ends up being that base value. So when you take the square root of anything squared, because squaring and square roots are inverses, they cancel each other out and we are just left with that base, which is x. Another example, if we take the square root of 3 squared, this is just going to be 3 because the squaring and the square root cancel out. All right. And we're going to take a look at what are perfect squares, right? Perfect squares, it's really helpful to kind of have this list pretty familiar. I would definitely recommend knowing the first 10, easy to identify, but knowing the first 20 can be super helpful. So 1 squared, remember when we're squaring a number, we're just multiplying it by itself twice. So 1 squared is 1 times 1, which is 1. 2 squared, which is 2 times 2, gets us 4. 3 squared, which is 3 times 3, gets us 9. Notice the pattern. 4 squared, which is 4 times 4, gets us 16. Right? We're just using multiplication to find these perfect squares. 5 squared is 5 times 5, which is 25. 6 squared is 6 times 6, which is 36. 7 squared, 7 times 7 gets us 49. 8 squared is 8 times 8, which gets us 64. 9 squared is 9 times 9, which gets us 81. And 10 squared is 10 times 10, which is 100. So those are the first 10 perfect squares. Super helpful to have those locked in your brain. We want to be able to identify them when we see them. If we continue to go, 11 squared is 11 times 11, which is 121. 12 squared is 12 times 12, which is 144. 13 squared is 13 times 13, which gets us 169. And 14 squared is 196. 15 squared, 15 times 15 is 225. Now let's look at the calculator for the last few. If I did a 16 squared, I end up with 256. So I'm just typing in the number 17, and then I'm hitting my a squared button to square it. That gets us 289. As our numbers get bigger, our products are going to get bigger as well. 18 squared is 324. 19 squared is 361. And finally, 20 squared is 400. So pause the video whenever you need, get the information that you need on the slide, and when you're all set, push ahead to slide 5. Nice job, everyone. So these perfect squares, we're definitely going to be using them and identifying them as we're working through simplifying our radicals. So we want to get comfortable with this list. And I put this list in the study guide for the module as well, so you can always have that up and reference it whenever you need to. On slide 5, you're just kind of checking in with how well you know your perfect squares. Maybe they're super familiar to you, maybe you haven't looked at them ever. Just let me know where you are identifying right now in this moment. This is going to change as you get more practice and more familiar with them, but just kind of notice how you're feeling right now. And then we're going to go and look at our perfect cubes next. So a perfect cube is a product of 3 equal integers. So when we're cubing something, we think of a dice like a cube has, a typical standard dice has length, width, and height. It has 3 dimensions. That's why it's called a cube. So we're taking a number and multiplying it by itself 3 times. 2 times 2 times 2 is 8. So 8 is a perfect cube, which means the cube root of 8 is just 2, because 2 times 2 times 2 gets us 8. 27 is another perfect cube, because 3 times 3 times 3 equals 27. So the cube root of 27 is just 3. Right? And again, if we look at this as the cube root of 2 cubed, because 8 is 2 cubed, we're just left with that 2. Cube root and cube are always going to cancel each other out. They are inverse operations, just like square root and square. 4th root and 4th power. 5th root and 5th power. Whenever we can match the root and the power, they can cancel each other out. Okay? Let's look at slide 7. We're going to make our perfect cube list. So now we're multiplying the base by itself 3 times, right? Because we're cubing it. So 1 cubed is 1 times 1 times 1, which is just 1. 2 cubed, as we just saw, right? 2 times 2 times 2 gets us 8. 3 cubed is 3 times 3 times 3, which is 27. Oops. Beautiful. 4 cubed is 4 times 4 times 4, and we can type that into a calculator as 4 times 4 times 4, and we would get 64. We could also type it in with the exponent, so for 5 cubed, I'm going to be 5, raise it to the 3rd power. So the way that I raised it on the calculator, instead of just hitting the squaring button, next to it there's an A to the B button, and you can type exponents, and I made that exponent a 3 because I was cubing it. You can also hit Shift, hold down Shift and hit 6 to type an exponent. So 6 cubed gets us 216. I definitely recommend practicing typing these into your calculator, making sure that you feel nice and comfortable with it. 7 cubed, 343. 8 cubed is 512. 9 cubed gets us 729. And finally, 10 cubed gets us 1,000. So these are our first 10 perfect cubes. So take your notes, get what you need, and push ahead to slide 8 when you're ready. And on slide 8, you're just kind of checking in with like, how did you feel about perfect cubes? Do you feel confident being able to make that list on your own? Is this totally new to you? You've never seen this before. Wherever you're at is exactly right, but just check in with yourself on slide 8. And when you're ready, we can push over to slide 9. So just like addition and subtraction are inverses and really related to each other, multiplication and division, inverses, very related to each other, roots and powers are also related and inverses of each other. So we use this information and we can rewrite an expression as having a power or in its radical form. So we're going to talk about how to go back and forth between those two types of forms. So again, we have our exponential expression, which gives us something that looks like this. We have a base of a, and we're raising it to an exponent. And that exponent is m over n. So what that means is power over root. This is a super important little thing to remember for this NQ2 lesson, power over root. So the power is m, the root is n. So when we're rewriting it as a radical expression on the right, notice our power became m and our root is n. So these are the two different ways that we can write an exponential expression. We can write it as an exponent or we can write it as a radical. Okay? And we're going to practice a bunch of doing these two different methods, starting off on slide 10. So up in slide 10, we have our exponent form, and we're going to turn it into radical form. So at the top of your screen, you might write power over root to remind yourself. That's what we want to be thinking when we're working through these problems. So our base is m, so I just write m first. I just take that m and I write m. My power is 2, so I'm putting a 2, and my root is 3. Power is 2, root is 3. For the next one, our base is a. Notice I just first grabbed that letter a, that's our base, whether it's a number or a variable, but that's what's being raised to the power, so we call it our base. Power is on top, our power here is 3, and our root is 2. When we're doing a square root, or when the root is 2, we usually won't put the little 2 number outside. If you see a root symbol without a number, it's assumed that it is a square root. So that's just something to note. We're not usually going to see that number 2 on the outside. It'll just look like this, and we know that that's the square root. Okay. One more here. X is our base. And our power is the number on the top of the fraction, which is 2. And we're doing the 5th root. Perfect. Down below, power over root, but writing it as now in exponential form. Well, n is our base. I don't see any power with n, which means there's like an imaginary 1 there. So the power is actually 1, and our root is 3. For the next one, we have a b. Our power is 2, and our root is 3. So it's a b to the 2/3. And then finally, we have the square root of 25 and the square root of a to the 6. So remember, we can always split this